Hi, and welcome everyone to this week's lecture on special considerations of implants, devices, and biomaterials. So far, we've talked about the molecular forces that dictate the bulk and surface properties of materials. We've talked about a different variety of materials, both within lecture and then also through the student lectures on specific materials that are commonly used in biomaterials engineering. And then also we've gotten insight on novel research, even at the academic and clinical level, through our journal discussions. After that, we also discussed the lengthy evaluation of biomaterials and what constitutes a biocompatible or bioincompatible material. Now we're getting into the third section of our textbook, which really describes how you bring about a novel biomaterial through the clinical process and some of the special things that you have to consider when trying to get something to market. Chapter 2 of Section 3 of the book talks about the regulatory process in detail, and that'll be one of our later lectures. This particular chapter in the book, though, discusses some of the special considerations we have to make both during the preclinical stage when we're translating a device from the laboratory to a commercial setting, and then also some of the analysis that we do during a post-market analysis, retrieval studies where we can look at implants and biomaterial devices even after they've been improved, both for the refinement of biomaterials and second generation versions of those devices, but also as a failure analysis that can elucidate some of the failure mechanisms that we wouldn't see in a much more controlled preclinical in vivo setting, and then also during a controlled clinical setting as well. So let's get into it. Now, one of the first considerations that we're going to look at is the sterilization process, which is simply put a process that removes, kills, or eliminates all organisms and biological agents on a particular device. Now, the reason that we're looking at sterilization in this chapter goes beyond the simple obligation of a manufacturer engineer to have to deliver a sterile product. It's the unique consideration that these sterilization processes have the ability to cause significant effects to a biomaterial, not only their bulk properties, but in particular their surface properties, as these are the areas that are exposed. And biocompatibility tests are heavily sensitive to surface properties of biomaterials, as we learned in previous chapters. However, unlike those tests that we've considered previously, sterilization processes only come up once you start the translational process of bringing a device from a laboratory to a commercial setting. So first we'll talk about some of these processes in length, and then we'll talk about their effects and potential compatibility or incompatibility with biomaterials. Now, there's 2 points in which you can achieve sterility. One is through a process called terminal sterilization, where biomaterials are handled in non-aseptic conditions throughout the process of manufacturing them, putting them together, and packaging them. And it's only at the terminal stages of the process, at the very end, once they've been packaged, where they undergo one single sterilization cycle. Now, the current regulatory expectation, what's called the sterility assurance level, of a blood contacting medical device or implant is to produce only one non-sterile device out of 1 million. Sometimes see this written as just 1e to the negative 6 or 1 over 10 to the 6. Which sounds incredibly high, something that of course patients will really like to hear, although it sounds almost unfeasible from a manufacturing standpoint. And the fact is that that's not actually true. It's actually quite easy with some of the methods that we're going to talk about in the next few slides to achieve this quite feasibly. The other means of achieving sterility is to go through a process called aseptic processing, where every step from beginning to the end stage is done under aseptic and sterile conditions. This is where you have to imagine work being done in clean rooms by engineers and technicians in full body clean outfits, handling the product from the beginning stages, the putting together the device, putting in the material packaging, and sealing it until it's off and shipped for delivery. Now, because this process is much more difficult, the sterility assurance level is 3-fold lower than that of terminal sterilization, only one non-sterile device out of 1,000. Now, while this sterility assurance level sounds better for the manufacturer because it might be easier to achieve, and perhaps not so desirable for the patient, it's actually incredibly difficult to achieve because aseptic sterilization is itself a very difficult process. It requires quality control measures to be demonstrated and effective at each of the processing and handling steps. It's because that there's a high risk of contamination at each one of these steps, as opposed to terminal sterilization processes can be totally handled under much less rigorous conditions under the fact that you're sterilizing the product at the very end of the cycle, not having to handle it aseptically throughout the entire cycle. And these quality control measures are not only much more difficult, but they're also much more expensive for the manufacturer. Not only is it more difficult and expensive on the manufacturing side, but the FDA recognizes the difficulties in maintaining these sterility levels all throughout the entire process. So the FDA even requires manufacturers to demonstrate that they've exhausted all potential terminal sterilization processes and that their device is not compatible with these standard sterilization methods. Therefore, only aseptic sterilization processing is a viable choice. Some common devices that have to go through aseptic sterilization methods are biologics, combination devices that have not only devices but drugs as well, and then also tissue engineered devices. Now, about half of all terminally sterilized devices undergo radiation sterilization. So I want to provide a little context on the dosage of radiation that these devices receive. So for instance, a typical X-ray gives a dose of about 0.7 milligrays. A pelvic CT scan is about an order of magnitude higher at 8 milligrays. Then we start seeing the first symptoms of acute radiation poisoning a few orders of magnitude above that in the 5 to 10 gray dosage. Devices that receive radiation sterilization undergo doses of around 8 to 35,000 grays. So if you're keeping count, that's almost 6 or 7 orders of magnitude higher than a relatively high dose of a pelvic CT scan. So this is literally lethal within seconds. Because of these incredible doses, a number of safety precautions have to be taken into account, such as using thick concrete, lead, and water shielding to prevent operators of these processes from experiencing the high radiation doses. There's also a series of robust interlocks that prevent users from being in the same area or rooms where these devices are being radiated. And there's also the concern with the generation of ozone, which is just the radiation hitting oxygen in the air and causing this really toxic gas. So there's a number of ventilation mechanisms and also ozone monitors in the areas where radiation sterilization is occurring. Now, the most common radiation sterilization method is gamma sterilization, which accounts for 80% of all radiation sterilization processes and about 40% of the total terminal sterilization process. This method utilizes cobalt-60, which decays into nickel, giving off thus an electron, and then the potent gamma particle. These gamma particles penetrate cells where they oxidize and create free radicals that cause the scission of microbe DNA. One big disadvantage is that they also size or cross-link polymer chains as well. Now, from a process standpoint, one of the biggest advantages of gamma sterilization is that gamma rays are incredibly powerful and can penetrate uniformly through very long distances. So you can have an odd-shaped device with uneven, ununiform surfaces, and yet the gamma particles are going to penetrate and uniformly distribute themselves and kill microbes in all areas of the device. A processing disadvantage is that the dosing can take many hours to achieve, so it's not a quick one-and-done process. Also, one thing I'd like to point out here is that while this source, cobalt-60, is itself radioactive, the gamma rays do not make the final product radioactive. So there's no radioactive components to the device once it comes off the sterilization process. I found a pretty great clip online that demonstrated the gamma sterilization process, so I'm going to take a pause from the lecture and show that video right now. Enjoy.
The process begins when unopened boxes or other containers are retrieved from the secure, non-processed side of the warehouse. This area typically includes a fence or physical barrier between the non-processed products and those that have completed the irradiation process. Products are carefully loaded onto a material handling system. They are usually put inside aluminum carriers or totes. Each load is designed to ensure the specified dose is delivered. Then, process monitoring devices called dosimeters are placed at previously determined points on the product to measure the delivered irradiation dose. Next, our specially trained and certified operators enter and verify the product-specific cycle parameters in the control system, and the cycle begins. The carriers travel by conveyor through a concrete maze that separates the non-processed area from the irradiation chamber. Inside the irradiation chamber, the cobalt-60 isotope, often called the source, is contained in encapsulated pencils that are carefully arranged in a specially designed rack. When not in use, the source rack is submerged in a storage pool of deionized water. This shielding allows the production and maintenance teams to safely enter the chamber as needed. With the gamma source rack in the raised position, the carriers enter the irradiation chamber. Each carrier passes by both sides of the source rack, ensuring even exposure. Length of exposure varies by product and predetermined dose range. After a carrier is exposed for the designated time, it exits the chamber through another concrete maze and moves into the secure, processed side of the facility. Here, the processed product is unloaded and the dosimeters are carefully removed and prepared for review. Product is then palletized and shrink-wrapped. A label is placed on each pallet indicating the product is processed, and pallets are stored in the processed side of the warehouse. After processing, specially trained employees visually inspect each dosimeter to make sure it was not damaged during the irradiation process. Dosimeter measurement is critical. The gamma irradiation process is not complete until the dosimeters are read and approved. Then, the dosimeters are placed into the dosimeter measurement device for measurement of response, which in turn is used to calculate the dose delivered to the product. Upon completion, a technician will e-sign the gamma dose record. Then, the gamma dose record report is electronically signed by a member of the planning team. Finally, once the quality team verifies that all the customer-specific processing parameters have been met, the product is now ready for shipment.
Another radiation sterilization method is called electron beam sterilization, or more simply, e-beam sterilization. This method accounts for 20% of all radiation sterilization processes and 10% of the overall terminal sterilization process. This process uses a variety of different technologies to accelerate electrons to the 0.2 to 10 mega electron volt range, producing high energy beta particles that emit and then penetrate into the device that you want sterilized. One of the big advantages of this is that it doesn't use any radioactive components. These electron accelerators are kind of like lamps that can be turned on and off without the use of a radioactive device that themselves produce radioactive beta particles. One of the big advantages with this method is the time that it takes to e-beam something is on the order of minutes, unlike gamma sterilization, which takes many, many hours. And this, therefore, can limit the oxidative degradation because the radioactive source isn't producing free radicals in the terms of ozone, so you don't have those particles degrading your biomaterial, whereas that is a possibility with gamma sterilization. However, one big disadvantage is that electrons or beta particles have a much smaller penetration depth compared to gamma particles. So you can't just have a single source that beams these electrons on one side of a particle and hope that it reaches all the nooks and crannies of your particular device. You have to undergo a process called dose mapping, where you look at all sites of your product using dosimeters and you evaluate the minimum and maximum dose received on all geometric areas in order to ensure that all areas of your biomaterial have received the proper radiation dose in order to become sterile. Particularly for devices that are susceptible to e-beam sterilization for degradation, this is a pre-manufacturing step that has to be considered and evaluated before you can settle on a particular sterilization method. A third method that represents a rather insignificant percentage of the terminal and radiation sterilization market is X-ray sterilization, which is sort of a hybrid between e-beam and gamma radiation. We say that because it makes use of electron accelerators in the same way that e-beam sterilization methods do in order to produce X-ray photons, which are very similar to the photons produced in gamma sterilization. The gamma particles themselves are photons. So because of this, it has some of the identical penetration and depth advantages of gamma sterilization, and also has the advantage of e-beam sterilization where there's no part of the process that's actually radioactive because they use these electron accelerators as opposed to a radiation source. Now again, I'll point out that in all these processes, though there's a radiation particle involved in the sterilization of these devices, the devices themselves do not become radioactive. Now, in all of these processes, something that has to be measured as part of your method validation is called the dose uniformity, which is the ratio of the maximum dose that a product receives to the minimum it receives during a given cycle. By definition, the dose uniformity is always greater than 1. And for some small products with relatively little packaging receiving gamma sterilization, we can assume that it's going to be pretty close to that 1. And then for other processes, rather large, bulky packed products that undergo, say, e-beam sterilization, this can be a lot more variable and can be much greater than 2, for instance. For devices that are somewhat susceptible to degradation through radiation sterilization methods, there's a certain balance that needs to be achieved in all parts of a device receiving the minimum radiation necessary to achieve sterility, but also making sure that, for instance, devices with a high dose uniformity, that the maximum dose received on certain parts of the devices doesn't exceed some sort of degradation threshold for that particular device. If so, the product packaging or method needs to be reconsidered. The second type of terminal sterilization process that we're going to talk about is ethylene oxide treatment, which accounts for 50% of the terminal sterilization market, so equal to that of all radioactive sterilization methods combined. This gas method requires products to be packaged into a microbial resistant but still penetrable barrier that allows the ingress and egress of both ethylene oxide and water vapor into the device. So if you ever see a medical device or even a sterile laboratory package that has sort of a paper-like porous membrane that you peel off to then get your particular device or instrument, then it was likely ethylene oxide treated as opposed to radiation treated. The process is rather long. It could take anywhere from 6 hours to several days, and it operates at a range of temperatures much higher than room temperature, so anywhere from 46 to 65 degrees Celsius, and also notably a high amount of humidity, which is going to come in a factor when we talk about the hydrolysis of certain polymeric biomaterial devices. So the humidity can be either from 30% to even up to 90% humidity. The gas works by penetrating cells and causing the alkylation of amine groups on DNA, rendering it useless. And the moisture facilitates ethylene oxide penetration and microbe interaction. So these devices have to be humidified before the ethylene oxide and during the ethylene oxide treatment in order for it to work. Now, ethylene oxide gas is obviously toxic, which is what we want. We want it to be effective against microbes, hopefully not humans. Unfortunately, it is, so a lot of safety precautions have to be taken into account. It's also carcinogenic and also notably incredibly explosive. I have a small little picture here of the 2004 Sterigenics explosion in Ontario, California, not Canada. And in fact, the next slide, I'm going to play a video of this, not only this treatment process, but that goes into this explosion and what exactly happened. So because of these safety precautions, workers are required to wear respirators when working with this or near the gas, and then products even have to be aerated after they're treated so that residual ethylene oxide levels fall below acceptable limits. In fact, biocompatibility tests are done after sterilization methods in part to look for the toxicity of residual ethylene oxide amounts. This is less of a concern for radiation sterilization because no radioactive particles are actually left on the device after they're treated, but that can't be the same for ethylene oxide treatment, so this has to be tested post-sterilization. So now I'll show a video on ethylene oxide treatment that gives you an overview of that process, what parameters have to be taken in place, and how it's actually done. So enjoy.
Products arrive at the plant, prepackaged and stacked on pallets, ready to be sterilized in large steel chambers. The plant contains 8 sterilization chambers, operated and monitored by personnel using a computer system in the control room. Packaged medical products are added to the chamber and the doors are sealed. The chamber is then filled with ethylene oxide, which penetrates the packaging over a period of several hours, killing any germs and sterilizing the products inside. After the sterilization phase, ethylene oxide is removed from the chamber and the packaged products in several steps. First, about half the gas is pumped from the chamber to a pollution control device called a scrubber, where it is removed by chemicals. Next, virtually all of the remaining ethylene oxide is removed in a step called gas washing. This involves injecting air and nitrogen into the chamber where they mix with the ethylene oxide. This mixture is then pumped from the chamber to the scrubber. This process is critical to reducing the concentration of ethylene oxide to below explosive levels, and is repeated several times until there is only a trace amount of ethylene oxide remaining. This trace amount of gas is not explosive, but it is toxic and must be removed by ventilating the chamber before workers can enter. The front door is raised a few inches, which automatically opens a vent at the rear of the chamber. Air is drawn through the chamber to another pollution control device called a catalytic oxidizer. Once the air enters the catalytic oxidizer, it is heated as it passes over open flames. Any remaining traces of ethylene oxide are removed as the air passes over a metal catalyst. After the chamber has been ventilated for several minutes, operators can safely enter to remove the products.
Great, so that's a nice video about the process. If you want to continue on with that video and see what happened the day of that particular plant's explosion, please hit the link in the description of the video. Now, as I alluded to at the beginning of this chapter, sterility isn't the primary objective from a biomaterial engineering standpoint because it's easy to achieve, and if that was the only thing that we were concerned about, we could simply have much longer radiation cycles or ethylene oxide cycles in order to achieve what we want. The main concern from our perspective is material compatibility. So this will tie into a lot in the degradation of materials chapter that we're covering as well. As I said before, radiation sterilization methods produce a lot of free radicals that in part governs the mechanism that causes their sterilization method. However, also has the ability to cause oxidative degradation of polymers. And not only that, the radiation itself can both size polymer chains, meaning to break them apart, and also induce cross-linking in the same way that we sometimes do UV cross-linking through radiation. So for instance, polyethylene, PE, is actually cross-linked through this process. So the polymer that you put into a package actually gets a higher molecular weight after you undergo the sterilization process. These kind of changes, of course, can change the bulk properties of the material, likely in detrimental ways, since you've already validated that particular product at the benchtop and laboratory setting, and you're just trying to get it sterilized. You're not trying to optimize it further through this particular process. Other polymers that are particularly affected by this is PTFE, fluoropolymer like the brand name Teflon, then polyacetyls, polypropylene. PMMA experiences less bulk property changes than it does this sort of degradation that produces a yellow or brownish discoloration. Of course, this material is commonly used in intraocular lenses, so you do not want discoloration associated with this particular polymer. PLJ also demonstrates significant molecular weight reductions because the radiation will actually size those polymer chains. The ethylene oxide gas, on the other hand, is actually a rather benign gas when it comes to materials properties, meaning most biomaterials see relatively small or insignificant changes when exposed to the gas itself. The more harmful side product of this process is actually the humidity and elevated temperatures and the time that the biomaterial experiences those. So because of the high humidity, we want to think of polymers that undergo hydrolysis or degradation through contact with water. So certainly think of polystyrenes and polyacrylates like polymethyl methacrylate, PMMA again. Now, because of these possible material incompatibilities with these sterilization methods, it's important to test the devices during their development and translational process to the commercial scale at the maximum acceptable sterilization dose and the most challenging process parameters. So that means if you're considering ethylene oxide, you want the most humid environments with the maximum acceptable time for the exposure to the particular devices. For gamma and E-beam sterilization, you want the highest maximum dose, even much more than would needed to be achieved sterility. You want to make sure that even the most minimally dosed areas of a device can meet up to the demand of the material compatibility. Now that the sterilization process has been considered, the last and second special consideration that we're going to look at for this particular chapter is implant retrieval and evaluation. This can occur at a number of different stages throughout the device design, in both the preclinical, meaning animal stage, clinical, where you have it in humans, and then continuing on with humans in the post-clinical and post-approval process once the device is out in the commercial and real-world setting. Now, the implant retrieval process provides an opportunity to identify the modes, interactions, and mechanisms that lead to the success or failure of a medical device under end-use conditions. Now, the latter is particularly important because this is information that we can't get from just a benchtop setting. This is not a bulk surface or material property of that particular device. This has much to do with the interaction with a particular end user as opposed to the material device design itself. Now, during a retrieval process, there's a few things that engineers want to analyze to determine the outcome or what factored into the outcome of a medical device. The first is the biomaterial and device design itself. The second is patient-specific functional anatomies and pathology, in a sense, their response to that particular device and how that affected the device itself. And then lastly, the technical aspects of implantation. Now, in the last point, I mean the implantation of the particular device by a surgeon, or really any key technician, interventionalist, like a cardiologist or radiologist, whoever is implanting that particular device that's interacting with a human. This latter point is particularly a key difference between devices and drugs, and that the efficacy of a drug is usually not dependent on the user, which is either the surgeon or the patient itself, and how they take it and administer that particular drug. There's certainly complications with patient compliance, which has more to do with the therapy or the regimen as opposed to the actual drug itself. Now, implant retrieval can occur at a number of different stages. It can be retrieved after a successful run by the device in a particular patient that maybe no longer wants it anymore. It can occur after the failure of the device and it has to be removed surgically, like through reoperation, or the patient can actually die, whether that death is caused by the device or through other means. Surgeons still have at that point an opportunity to retrieve and take out the implant. In instances of death or even faulty or failure of a particular device, the amendment to the United States Medical Device Act in 1990 requires that both the healthcare personnel and hospitals report any complications that result in death, serious illness, or injury to the FDA and possibly, but not necessarily, the manufacturer. Now, there are a number of problems associated with this approach. One, that it's very difficult to determine that if a death occurs, if it is associated with the prosthesis or device at all. Furthermore, few hospital pathologists have the appropriate training, motivation, or even necessary resources to do a complete and sophisticated analysis on the retrieved implants. Now, implant retrieval and device failure analyses at different stages have their own different advantages and disadvantages. The advantages of doing retrieval analyses in the preclinical studies, like through animals, are as follows. They can have more detailed monitoring because you're keeping closer track of the animals, whereas humans, you have to let them go on about their lives. There's a higher control of environmental factors and other variables because you are yourself controlling the study. There's the ability to assay laboratory parameters a lot more frequently. For example, you can analyze blood coagulation factors or certain proteins emitted by the body as a monitor of the inflammatory process. You have the ability to either non-invasively or even potentially invasively monitor the device in situ. This could be through radiographic imaging, ultrasound imaging, a number of different ways. There's also a host of number of analysis techniques that you can do in vivo that simply aren't feasible in the in vivo setting, such as the injection of cells, imaging methods like contrast agents, radio labels that are certainly toxic to humans, but you're allowed to for in vivo purposes. After the retrieval of an implant, you can also analyze the leftover tissue because the animal is likely sacrificed at that point, so you can do all the tissue staining and histology samples that aren't accessible to live humans. You can also allow for concurrent control implants. This is something you simply can't do on the clinical level, put in benign implants for people like through a blind to double-blind study. You just can't do it. There's also certain animal models that allow advantages on the time scale in comparison to humans. So for instance, sheep models are often used to simulate 5 to 10 year calcification process just due to their natural anatomy and physiology of bioprosthetic heart valves that are usually just measured on the order of 4 to 6 months within the animal itself. Now, on the flip side, human studies and the clinical and post-clinical retrieval study offer their own advantages, such as longer duration times are possible. You simply can't do year-long studies in the preclinical process. That there's no iCook board that will allow animals to be subject to that kind of treatment. There's also the most realistic biocompatibility model. You're comparing humans with humans as opposed to trying to make correlations of animal models to humans. There's also the advantage of the uncontrolled environment, something that might be a disadvantage in the in vivo stage. You're allowing all the real-world possibilities that are generated by humans in an uncontrolled environment to give you a more realistic scenario of how your device is performing. There's also unique patient-specific factors that can impact the performance of a particular device. In fact, there's a field of study of this called biomaterial genomics, which is a study on how genes affect the outcome of biomaterial devices, a really cool field. This discipline makes use of what are called biomarkers, which is some sort of measurable substance whose presence indicates a particular biologic state and condition. We see these a lot with proprietary assays that measure biomarkers for cancer or maybe Alzheimer's. I'll now go over a few specific examples of implant retrieval process to kind of highlight the clinical utility of this type of analysis of biomaterials and their devices. So the first example we're going to look at is sort of the evolution of prosthetic heart valves. So in the beginning, in the 60s, this device used a type of design called a caged ball valve. As you can see in the pictures, it's literally a ball within a cage that under one direction of flow opens the portal because the ball is at the very end of the cage. And then under reverse flow conditions, the ball would actually block the portal that normally allows blood to flow past it. Now, early designs demonstrated both thrombus and degradations as complications of this particular device. Implant retrieval analyses noted that the silicon ball within these devices degraded significantly over a relatively short amount of time. This was due to the lipid absorption of the silicone balls, and this was virtually eliminated just through simple improvements of the silicone curing process. To improve upon the thrombus forming complications, a cloth-covered ball and cage design was introduced to encourage tissue ingrowth, which thereby decreased thromboembolisms. Thromboembolisms were further reduced with the introduction of the new type of device design called the tilting disc variation. During different trials of the coating of these tilted discs, retrieval studies of the carbon valves recovered at autopsy or surgery were analyzed via SEM or scanning electron microscopes and indicated that in comparison to Teflon-coated discs, these pyrolytic carbon discs showed minimal abrasive wear. Other complications that arose from this type of design include the fracture at the welding points of the disc that actually resulted in the release of the disc. Retrieval studies showed that this was caused by the calcification of the material, and thus sheep were recruited to look at accelerated calcification, wear, and fatigue tests, utilizing increased exercises and cardiac activity of the sheep in order to improve the testing methods. Next, the development of a low-friction total hip arthroplasty by Charnley is a classic example of how implant retrieval can yield important clinical information which impacts implant materials and design. Now, the original choice for the cup was a low-friction Teflon-like PTFE polymer. Now, just like we saw similar to the heart valves, Teflon has a very high wear rate. This resulted in many of these devices failing after only a couple years due to the severe wear and the intense inflammatory reactions their weared products created. Teflon was then replaced by ultra-high molecular weight polyethylene that showed increased wear resistance in comparison to Teflon. Now, in the development stages of utilizing this polymer, many different things were attempted to try and improve its mechanical properties, including different heat pressing techniques and fiber reinforcement, but retrieval studies demonstrated that these improvements were not nearly as effective as in other PE applications. More notably, however, were that the physical and mechanical properties of polyethylene were altered by ionizing radiation due to the generation of free radicals during a sterilization cycle. Oxidation showed detrimental effects to ultra-high molecular weight polyethylene, leading to a decrease in some factors like elongation of failure, an increase in elastic modulus, and a decrease in fatigue cracking propagation resistance. All of these resulted in the premature failure of some of these components in the devices. Later retrieval studies showed that improvements to device design by incorporating antioxidants, note my personal choices would have been blueberries and those from pomegranates. However, biomaterial engineers tend to use something a little bit more practical like vitamin E. These antioxidants showed improved resistance to oxidative degradation in vivo. So that's today's lecture. We're also going to talk about degradation mechanisms a little bit more in depth in the next chapter, and then we'll get on to the regulatory approval process. So thanks for listening.